So I'd like to talk about why we essentially have the approach we do with when dealing with stoichiometric reactions. It's a very long process. Sometimes it can even be a little confusing and a little complicated because we're not just using one conversion factor. We're essentially stringing along multiple conversion factors, and it may seem as though insofar as doing so, we may lose sight of why we're doing what we're doing. So I was hoping that this video could serve as sort of an in-depth explanation as to why we would even bother with converting with the conversion ratios or factors that we mentioned before in the previous parts for stoichiometric reactions. And the idea, and this is sort of an example that I have here. This is an example which is going to demonstrate sort of why we go through the route that we do. But the idea is really to understand in general terms when dealing with problems like this, why our approach is so effective. So if you could ignore basically everything on the board right now and just really think about this conceptually, if you have, and this is sort of where I'm trying to divert your attention to, not the content, but instead perhaps just simple illustrations, overarching illustrations, if you will. If you had a compound, right, and this is a compound in terms of grams, and then you had another compound, right, in terms of grams, or actually let me put some space between here. You have another compound in terms of grams. There really isn't any conversion factor which can essentially allow us to go from grams of one compound to grams of another compound, right? We know that the molar mass conversion factor tells us that we can take the molar mass of the compound and then convert that to we can take the molar mass of the compound, and that would give us a relationship, and that relationship would be between grams of the compound to moles of the compound. And so when speaking in context of compounds, that's essentially the one of the only conversion factors that we have at our disposal, which is exclusively molar mass, which allows us to express grams of that compound to moles of that compound. But really, if you sort of look at the overall question here, the question is, how can you go from grams of a compound to grams of another compound? And why we bring in the molar mass, why we even care about having the molar mass of this compound and even of this compound, is because the mole is it's sort of a convenient method by which we can eventually start talking about grams. And I'll sort of demonstrate this here with this question. But if we're talking about a compound and we convert that compound, and this is of course in relation to another compound. If we have a compound and it's in terms of grams, and we essentially convert it to its to moles, and in order to do that, we'll need the molar mass in order to do that. But if we convert it to moles of that compound, then we can make a ratio. I mean, if we have the balanced chemical equation, we can make a ratio of moles of compound 1 to moles of compound 2. And what that would allow us to do is it would allow us to say, okay, well, moles of compound 1 is to moles of compound 2. And so this is sort of a relationship that we were able to establish by converting both of those compounds which were in grams basically into moles. And of course, this happens proportionately with the amount of grams that we're given in the question. It's not just completely random, but once we have this ratio, moles of C1 is to moles of C2, C being the compound, what we can do there is then we can just work our way through basically grams, right? Because you'll notice that, we went from grams to moles, and then we can say, okay, well, how many grams is that many moles if we've effectively established sort of a relationship, then we can essentially, if I were to say, okay, moles of C1 is to moles of C2, then I could just ask the question, how many grams is that many moles of C2, right? Or how many grams is that many moles of C1? And then out would pop my grams in relation to moles of C1. So if that's confusing, hopefully I can illustrate. Hopefully I can illustrate with this example, but I would just like to reiterate what we were doing here, and we'll compare this with the approach that we take on the side. But what we were doing here was we were saying, okay, well, take your grams of compound 1, right, and convert it to moles, of compound 1, right? And then make a ratio between moles of compound 1 to moles of compound 2, right? And then after you have that, just ask yourself how many grams is that many moles of compound 2 in grams. So, this question, it gives us a balanced chemical equation. And it says how many grams of hydrogen sulfide are produced when 5.0 grams of hydrogen gas is used. So your starting point is 5 grams of hydrogen gas, which is H2. And we want to first establish a relationship between moles of hydrogen gas and moles of hydrogen sulfide. And the only way we can even begin to do that is if the amount of grams that we were given can be expressed as moles. Then we'll talk about expressing it in terms of the other compounds' moles. But as of now, we want to be able to express 5 grams of hydrogen gas in terms of moles. And we would need the molar mass conversion factor in order to do that. So the molar mass conversion factor, H2, how you actually find the molar mass of a particular compound is you essentially account for the atomic weight of the atoms or the elements in the compound, and you add them all together for how many atoms there are. So H2S, you have 2 hydrogen, and hydrogen has an atomic weight of 1.008. And then you multiply that by 2 because you have 2 atoms of hydrogen. And then you add that to the atomic weight of sulfur. And if you do that, you'll essentially get 34.08. So it is 34.08 grams per mole. So 1 mole, right, of H2 is equal to 34.08 grams of H2. And I could have, done this the other way around. I could have put H2 on the top, grams of H2 on the top, and moles of H2 on the bottom, but I wouldn't be able to cancel out my grams here. I wouldn't be able to cancel them out. And so now I'm left with moles of H2. And so if I were to stop here, that wouldn't really answer the question, right? The goal was to make a comparison between moles of C1, which I have, but I wanted the comparison to moles of C2. So imagine if I just had X moles of H2, right? And I want to I essentially want to express moles of H2 as moles of hydrogen sulfide. What would you do? Well, you would need Y amount of moles of H2 on the bottom so that they could cancel out. And you'd want to be left with Z amount moles of hydrogen sulfide, which is H2S, right? So we want a conversion factor which is exclusively between moles, which can allow us to cancel out the moles of H2, and we'll be left with moles of H2S. And the idea is that you can actually get this conversion factor, comparing moles of H2S to moles of H2 in the chemical equation, because the chemical equation, if it's balanced, can tell you proportionately how many moles of H2 were used to make H2S. And if you look at the chemical equation here, you can see that 3H2 makes 3H2S. So that is your conversion factor. So if you have 1 mole of H2, if you multiply that by 3 moles of H2 equals 3 moles of H2S, then your moles of H2 would effectively cancel out and you'll be left with moles of H2S. And then you have achieved this part of the chain that can allow you to compare moles of the first compound to moles of the second compound. But instead of going off and doing it at the side, it is sort of an extension, because at this point, right after you're done with this, after the math is done, after these cancel out, this number, whatever it is moles of H2. So instead of going off to the side, what you'll usually see is they'll just extend the conversion factor and they'll just hop on to using this conversion imposed on moles of H2. Right? Because that's what you're left with. You're always left with this guy here. So 1 mole of H2, and then that's your starting point. You don't go off and, do something else on the side. You just sort of extend what you were doing before and then move on to the next conversion factor. So if you put 3 moles of H2 here, as we discussed, and then 3 moles of H2S, right, which was the conversion factor that we were able to extrapolate from the chemical equation, then your moles of H2 would cancel out and you'd just be left with 3 moles of H2S. And so you were able to compare and sort of make this comparison. You were able to express what you were given in terms of moles of H2S. But again, moles of H2S is not what we want. We want grams of H2S, grams of hydrogen sulfide. And so, you ask yourself a question again, okay, well, this is my new starting point now, which is 3 moles of H2S, right? If you just had this, and sort of you're ignoring what we had before, but if you just had this, how would you what would you do in order to express this as grams of H2S? Well, you would want X amount moles of H2S to cancel out, right? And then after those would cancel out, you'd want to be left with grams of H2S, right? So you'd want to be left with Y amount grams of H2S. And so you're asking yourself, and you're looking through your conversion factors, like, do I have a conversion factor that can somehow get me from moles that essentially equates a particular amount of moles of a compound to its gram equivalent? And the answer always comes back to molar mass, because the molar mass of the compound H2S, if we look up here, okay, yeah, I believe that I was supposed to write the molar mass of H2 here, but I wrote 34.08. It's actually 2.02, small correction here. But back to sort of the original point, we have 3 moles of H2S. You want to express that as grams of H2S. And so you use your molar mass conversion, which says that 34.08 grams is 1 mole of H2S. So 34 you'd actually want to put your moles on the bottom, right? So 1 mole of H2S is 34.08 grams of H2S. And then what that would allow you to do is it would allow you to express your moles of H2S, which you've built up to this point, in terms of grams. But again, instead of going off to the side and doing all this here, what they do is they just extend. It's sort of a continuation of their conversion factors. They know that this is eventually all going to cancel out. this is all going to cancel out, right? Grams of H2 is going to cancel out with grams of H2. You'll be left with moles of H2. Then moles of H2 will cancel out with moles of H2. You'll be left with 3 moles H2S. So you're looking at your starting point in terms of here. That's your new starting point from where you. Like I was saying, that's sort of your new starting point. Where you pick off from, and you know you want it in grams. So this conversion factor is what you'd use. So you're like, okay, well, how can I cancel out my moles of H2S? I'll use molar mass. And 1 mole of H2S cancels out with moles of H2S. And you want to be left with grams. So you write your grams, and that would effectively cancel out and get you a particular answer, which in this case, let's see here, which in this case would be 84 grams of H2S. So you can see here that you could break the string of conversions apart and sort of do them separately, but that really doesn't save you a lot of time. It sort of interrupts or disrupts an otherwise smooth progression of conversion factor chains, which can eventually get you to sort of the end of the tunnel where you're left with what you want, if that makes sense.